So this is the second video I'm making about the epsilon delta definition. I thought I would be able to finish the topic in one video, but I wasn't able to, so this will be the second video. I was looking back at some of the earlier videos that I made, and I noticed that sometimes when I write, it doesn't come out very nicely, or like I don't write, I guess, very nicely. So I'm going to try to write in a more elegant manner, but if I'm not able to, I mean, just try to follow what is going on and what I'm saying, and then something like that. But I'll try to write in a nicer way. So this is going to be problem 16, page 96 in the book, which is in the description. And the problem asks us to prove the limit as x goes to -2 of 1 over 2 x plus 3. And it wants us to prove that the limit for this is 2. So again, just writing out based on the definition. Again, this is definition 2 on page 88. We have that we want for every epsilon, so for every epsilon, oh wait, there we go, that way. There exists a delta, okay, for every epsilon, there exists a delta such that we have 0 is less than the absolute value of x minus -2, so plus 2 in our case, is less than delta. Then we have that f of x, which in our case is 1, is a half of x plus 3 minus L, which in our case is 2. We want this to be less than epsilon. So we want to find a function that you give it epsilon and it gives you back a delta which satisfies this. So so this is the same as saying that we want the absolute value of a half x plus 3 minus 1, right, to be less than epsilon, or in other words, we want a half of x minus 2 to be less than epsilon. Is this a minus? No. Sorry, this is a plus, and this is a plus because it's minus 2. 3 minus 2 is plus 1. So, right, so this is the same as saying this, or it's the same as saying that x plus 2 is less than, x plus 2 is less than 2 epsilon. So if we make a delta, if we take delta equals 2 epsilon, we're going to have the absolute value of x plus 2 is less than delta, which is equal to 2 epsilon, right? In other words, the absolute value of x plus 2 is less than epsilon, so a half of this is less than epsilon. In other words, we're going to have that a half of x plus 1, the absolute value of that is less than epsilon, or in other words, we're going to have that the absolute value of a half of x plus 3 minus 2 is less than epsilon, which satisfies this. So you see, we started with this condition, x plus 2 is less than delta. We said the delta is always 2 epsilon. You can always make delta equal some constant or some number times epsilon, even x epsilon, if you're not trying to prove uniform continuity. So delta can equal like x epsilon or something like that. We're not going to get into that. So we have delta in terms of epsilon. We have this is less than delta, which is equal to 2 epsilon. So we have this is less than epsilon, this is less than epsilon, so this is less than epsilon, so we get this. So from here, from assuming this, we got this for epsilon equal to 2, for delta equal to 2 epsilon. And that's fine. So we figured out what delta is. So the next problem that I'm going to do is problem, let's do problem 18, because that I'm going to do the even problems. I hope it's clear to read it, whatever. I'm going to try to make my handwriting more elegant, but I don't know if I can promise anything. The limit as x goes, I guess there's really no point of making these videos if no one can read what I'm writing, but on the other hand, I'm just making them, I guess, because I'm bored. So, whatever. Why try that hard? No, I'm joking. Okay, so we want, again, we want for all epsilon, there exists a delta such that 0 is less than the absolute value of x minus 4 is less than delta, then f of x, so 7 minus 3x minus 5, because minus L, so plus 5. We want this to be less than epsilon. So we want to find a delta that we can then say that when this is true, this is true. So again, we're going to look at this first, try to interpret it in terms of delta, and then just write a little proof to show that if we have this, and we know our delta in terms of epsilon, then we have this. So what we want is we want negative 3x plus 13, no, not 13, 12, to be less than epsilon, or in other words, we want the absolute value of negative 3 times x minus 4 to be less than epsilon. Again, we're looking to transform this equation, this part at least, to something that looks like that, right over there, and then to compare delta and epsilon. So now we have the absolute value of negative 3 times the absolute value of x minus 4. We want this to be less than epsilon. Or in other words, we want the absolute value of x minus 4 to be less than epsilon over 3. So now if we take delta equals to epsilon over 3, so let's see how this will happen. So we're going to have x minus 4 is less than delta, because we're assuming that this is true. We're trying to get from a statement where this is true, so we're assuming that this is true, to this, and we're to this claim, right? Because this is a if this, then this. So we're assuming this, and we're trying to get this with the extra assumption that delta equals epsilon over 2. So we have x minus 4 is less than delta, which is equal to, that's a 3 to epsilon over 3, which is equal to epsilon over 3. In other words, we have x minus 4, the absolute value is less than epsilon over 3, or that 3 x minus 4 is less than epsilon, or that the absolute value of negative 3 x minus 4 is less than epsilon, which gives us that negative 3 plus x plus absolute value of negative 3x plus, plus 12 is less than epsilon, or in other words, we have that the absolute value of 7 minus 3x plus 5 is less than epsilon, so we get this. So assuming this, and assuming delta equals epsilon over 3, which again, we can make delta to be anything we want in terms of epsilon, because the claim is for all epsilon there exists a delta. So someone provides us with an epsilon, and we provide them back with a delta. And we can provide them back with a delta in terms of epsilon. So we get this claim. And so we get 7 minus, and so we get this, so we get that, so we just proved the limit. Next problem is going to be, so I did problem 8. So now I'm going to do problem, I'm going to only do the even problems. So I'm going to do problem 20. This is again on page 96. So problem 20 says the limit as x goes to 6 of x over 4 plus 3 is going to equal to 9 over 2. So now, so again, let's write out what we want. We want for all epsilon, there exists a delta such that if the absolute value of x minus 6 is less than delta, then the absolute value of x over 4 plus 3 minus 9 over 2 is less than epsilon. Right? That's what we want. So now let's find our epsilon in terms of delta in terms of epsilon. So this statement over here is the same as saying that we want x over 4, okay, 4 like that, plus 12 minus 18, just finding the common denominator. We want this to be less than epsilon, or in other words, we want x minus 6 over 4. We want this absolute value to be less than epsilon, or in other words, we want 1/4 of x minus 6 to be less than epsilon, or we want x minus 6 to be less than 4 epsilon. To be less than 4 epsilon. So what condition do we need to have this? What condition do we need to have that? Well, we need delta equals 4 epsilon, because we can assume this, that x minus 6 is going to be less than delta. And if we also assume that delta is equal to 4 epsilon, we're going to get this. So now from here, let's start with this assumption, and again, we want to end up with this. So we're going to have x minus 6 is less than delta is equal to 4 epsilon, or in other words, 1/4 of x minus 6 is less than epsilon, or in other words, x minus 6 over 1/4 is less than epsilon, or in other words, x plus 12 minus 18 over 4 is less than epsilon, or in other words, well, just getting to the end, x over 4 plus 3 minus 9 over 2 is less than epsilon, and this, again, is what we're looking for. So again, we assumed that x minus 6, the absolute value of x minus 6 is less than delta, and at the same time, we can say we want delta to be 4 epsilon, and from this assumption, we got down to the claim x over 4 plus 3 minus 9 over 2 is less than epsilon. The absolute value is less than epsilon. So that again proves that this claim, that the limit as x goes to 6 of x over 4 plus 3 is equal to 9 over 2. Okay. Next problem is going to be problem 22. So problem 22 asks us to prove that, the limit as, 22. X goes to negative 1.5. X goes to negative 1.5 of 9 minus 4x squared over 3 plus 2x is equal to 6. So again, when we write this out, we're going to have x plus 1.5 is less than delta, then 9 minus 4x squared is less than 3 plus 2x minus 6. And this is less than epsilon, right? So when we have this is less than delta, we want this to be less than epsilon. So the way to do this is, so let's see how this looks. So we're going to have, so 9 minus 4x squared is equal to 2x plus 3, and okay, let's do it the other way. 3 plus 2x and 3 minus 2x. And the way to realize this is simply, we want something that cancels with 3 plus 2x, right? That's clearly what we want. So what we're going to do is we are going to try to write it out in terms of, again, we're going to try to write it out in terms of 3 plus 2x times something is going to equal to 9 minus 4x squared. So what is this thing? So first I need the 9, so I'm going to put a 3 here. But then when I take 2x times 3, I get plus 6x, but I want to get rid of that. So, no, sorry, wrong place. I get plus, no, I get 4x squared. Sorry. So first I put a 3 here, and I get 3 times 3. So down, I'm just going to write what I get. I'm going to get 9. And then I'm going to get 2x times 3, which is going to be plus 6x. And then, so I want to get rid of that. So I'm going to take out 6x. And the way to do that is to just put a 2x over here. And now 3 times 2x is going to be minus 6x. And now you just hope it's going to work out, which it does in our case. 2x times negative 2x. Oh, so these, you get rid of that, is equal to negative 4x squared. So we have this equality. And that's pretty much how you figure out the equality. Now we can write that we want 3 plus 2x times 3 minus 2x over 3 plus 2x. We want this minus 6 to be less than epsilon, or in other words, canceling these, we want 3 minus 2x minus 6 to be less than epsilon, or in other words, we want negative 2x, 3 minus 6, so this is going to be negative 3 to be less than epsilon. So we want to take out a 2 now, so we're going to have negative 2 absolute value times the absolute value of x minus 1.5 to be less than epsilon. So in other words, we want the absolute value of x minus 1.5 to be less. We want x minus 1.5 to be less than epsilon over 2. And is there a minus there? No, because we took it a minus, so there's a plus here. So in other words, if we take delta is equal to epsilon over 2, then we have this is going to be less than epsilon over 2. So now let's see if it works. So basically the claim now is delta equals epsilon over 2 works. It will give us that if we assume this, we get this. That's what it will give us. So 1 second. No reason to erase it. Anyway, whatever. So let's see if that is correct. So let's assume that we have x plus 1.5 is less than delta is equal to epsilon over 2. So we're going to have x plus 1.5 is less than epsilon over 2, or in other words, negative 2 absolute value x plus 1.5 is less than epsilon, or in other words, negative 3x minus 2x minus 3 is less than epsilon. In other words, we're going to have, what was it? The absolute value of negative 2x. Okay, I think it was negative 3 minus 2x plus 6. Okay, it's going to be 3, and then this is going to be minus 6, right, is less than epsilon, right? From here we can get to here. And then we're going to get 3 plus 2x times 3 minus 2x over 3 plus 2x minus 6 is less than epsilon, right? Because we can just multiply both of the sides by 1 here. And so we're going to get 9 minus 4x squared over 3 plus 2x. Sorry. 2x minus 6 is less than epsilon. We are done. So that's how you do that problem. You're going to try to find delta in terms of epsilon over 2, and then you're going to assume this and try to come to here, try to get to here. And you can just work back on your steps. There are certain steps that get you what delta is in terms of epsilon. And that's just by seeing how this looks and trying to turn this, the absolute value over here, into this absolute value over here to look similar. So then you just work backwards through those steps, and you should be able to prove pretty easily what you're trying to in your epsilon delta definition stuff. Okay. The next problem I'm going to do is problem 24, which does not look very hard. Problem 24, same page. The problem states the limit is x goes to a of c equals c. So writing down the definition, we have x minus a for any a is less than delta, then f of x, in our case c, then c minus c is less than epsilon. Well, we don't even need to look at this. We know we're assuming, if you look at the definition, that epsilon is greater than 0. The c minus c, the absolute value of c minus c, is equal to 0. And 0, by definition, is less than epsilon. So we just get this. trivially. We trivially get c minus c is less than epsilon. And if you studied logic, it's true that if Q, then if P, then Q. If Q, then if P, then Q, and this is P, this is Q, and we have Q, right? We have Q over here, so we have if P, then Q. Done. Okay. So I'm going to do some of the, doesn't look like any of the other even problems are very difficult. I'm going to do, it doesn't look like any of the odd problems are very difficult. Fine, I'll just do some more of the even problems. I guess I'm going to end this video maybe at like 45. I don't know. We will see. So the limit, I'm going to try to prove that the limit is x goes to 0 of x to the third equals 0. So again, we want the absolute value of x minus 0, which is just x is less than delta. Then the absolute value of f of x minus L, which over here is x to the third minus 0, is less than epsilon. Or in other words, we want the absolute value of x to be less than the square root of epsilon. Can you do that? Yeah, that seems fine. So we want delta to be equal. All right, so yeah, this is the same as x times x, which is the same as the absolute value of x times the absolute value of x times the absolute value of x, which is the same as x absolute value to the third. So that seems fine. So anyways, we want the absolute value of x, to be less than epsilon. So we want delta to be equal to the square root of, to the third of epsilon. And now, well, let's assume that the absolute value of x is less than delta is equal to this. So then we're going to have x to the third is less than epsilon, or the absolute value of x times the absolute value of x times the absolute value of x is less than epsilon. Or in other words, the absolute value of x to the third is less than epsilon, which gives you this. So that's how you do that proof, and you would do basically the same exact thing for 25. Let's look at 23 for a moment. Problem 3. Maybe I'll do problem 23 and 21. So we have the limit as x goes to a of x equals a. So we want the absolute value of x minus a to be less than delta. Then we want x minus a to be less than epsilon. So if we just take delta equals epsilon, so we get x minus a is less than delta is equal to epsilon. So x minus a is less than epsilon, and we're done. We assume this, we got that. Okay. So now I'm going to do problem 21. We're given, we want to find the limit. X goes to 2, x squared plus x minus 6 over x minus 2 is equal to 5. So we want to prove this. So we're going to have x minus 2 is less than delta. We're trying to prove that if x minus 2 is less than delta, then f of x, in our case x squared plus x minus 6 over x minus 2 minus 5 is less than epsilon. We already looked at this equation before, and we said that x squared plus x minus 6 is equal to, I believe it was x plus 2, x minus 2, right? This is x squared, no, maybe plus, maybe minus, no, it's not this. What was it? It was x plus 3, x minus 2, right? Because this is x squared minus 2x plus 3x minus 6. So this becomes x squared plus x minus 6. So that was that. So now what we're looking for is x plus 3 times x minus 2 over x minus 2. These cancel. Minus 5 is less than epsilon. So we're looking for x plus 3 minus 5 is less than epsilon, or x minus 2 is less than epsilon. In other words, we want delta equals epsilon. Wow. Okay, yeah, fine. We want delta equals epsilon. So now let's actually do the proof now. So we're assuming this again, and we're trying to get to here. So we're assuming that x minus 2 is less than delta, which for us is equal to epsilon. So x minus 2 is less than epsilon. So that's the same as saying x plus 3 minus 5 is less than epsilon. Or in other words, that's the same as saying x plus 3 times x minus 2 over x minus 2 minus 5 is less than epsilon, right? This we get from there to there. And that's the same as saying x squared plus x minus 6 over x minus 2 minus 5 is less than epsilon, which completes the proof. Okay, that was problem 21. Let's do problem 19. We have the limit. Limit as x goes to 3, x over 5 equals 3 over 5. So, right, we're going to have x minus 3 is less than delta, then x over 5 minus 3 over 5 is less than epsilon. In other words, we want a fifth x minus 5 to be less than epsilon, or x minus 3 to be less than 5 epsilon. So we want delta equals 5 epsilon. So now to prove it, x minus 3 is less than delta is equal to 5 epsilon, or in other words, a fifth x minus 3 is less than epsilon, x over 5 minus 3 over 5 is less than epsilon. That completes our proof. Very nice. Let's do problem 27 and then problem 28. Problem 27. Okay, so we want to prove that the limit x goes to 0, the absolute value of x equals 0. Or in other words, okay, so we want x less than delta, then f of x minus L, which is x, absolute value of x minus 0, is less than delta. In other words, the absolute value of the absolute value of x is less than epsilon. Taking absolute value twice does not really change anything. We can just say the absolute value of x is less than epsilon, so we want delta equals epsilon. Looking over here, we're going to have the absolute value of x is less than delta is equal to epsilon, or the absolute value of the absolute value of x is less than epsilon, or the absolute value of the absolute value of x minus 0 is less than epsilon, which is exactly what we want. So that is problem 27. Let's look at problem 28. Problem 28, we have that the limit as x approaches 9 from the left of the square root of the whatever it's called, 9 minus x is equal to 0. We want to prove this. So now we're going to use a different definition. Because we're approaching from the left, there's a different definition for that from the epsilon delta definition. This is the third definition on page 91, and it states that the limit as x approaches a from the left of f of x equals L. This means that for every epsilon greater than 0, there exists a delta greater than 0, such that just for no absolute values in the domain. So we just have x minus delta is less than x is less than a, then f of x minus L is less than epsilon. So now, so let's just write it out with our stuff. So now we want 9 minus delta is less than x is less than 9. Then this 9 minus x minus 0, so just is less than epsilon. Or in other words, what we want is the absolute value of 9 minus x is less than epsilon to the 4th power, I believe. Or we can get rid of the absolute values and say 9 minus x is less than epsilon to the 4th power. So in other words, we want negative x to be less than epsilon to the 4th minus 9, or we want x to be greater than 9 minus epsilon to the 4th. So we can say that we want x to be less than 9 minus epsilon to the 4. So if we take, we can say, that's not what we're saying. What we're saying is that we want x to be greater than 9 minus epsilon to the 4, and obviously less than 9. So if you take delta equals epsilon to the 4th power, then we're done. Then we get this condition, meaning we go from this condition to over here because delta is equal to epsilon to the 4, and then just running backwards over here, we get to this claim, which means that we get here, which means that we fulfill what we need in order to fulfill, and we get from here to here. Okay. Next two problems are not very interesting, so I'm going to skip them. Okay, so the next problem I'm going to do is actually a little interesting, and it's going to be problem 36. So if we have, we have that, the limit as x goes to 2 of 1 over x equals a half. So we want to prove this limit, that this limit is true, that the limit is x goes to 2 of 1 over x is equal to a half. So we're going to have x minus 2 is less than delta, then 1 over x minus a half is less than epsilon. Or in other words, 2 minus x over 2x is less than epsilon. I'm just doing this because that this is just finding the common denominator, or in other words, 2 minus x over the absolute value of 2x is less than epsilon, or in other words, the absolute value of 2 minus x over 2x is absolute value of x is less than epsilon. So now we want this to be less than epsilon, right? Or in other words, we want so thinking about it, we know that for absolute values 2 minus x is the same as x minus 2. So we can rewrite this. What we want now is x minus 2 over 2 absolute value of x to be less than epsilon. Now this is what we get to assume that it's less than delta. So if this is less than delta, then this whole thing, let's just think, what is x minus 2 over 2 absolute value of x? Well, this whole thing is going to be less than, this delta over 2 and absolute value of x, but we don't have to, the absolute value of x, just the bigger x, the smaller this thing. So for x, and x is not going to be smaller than 1. X is not going to be smaller than 1 because that we choose a delta so close to 2. So we're going to choose it such that if we take x from delta, from 2 plus delta, from 2 minus delta to 2 plus delta, x is going to be greater than 1, right? If we make so the first thing we could say is just take a delta such that it satisfies this, such that delta is small enough, meaning delta is bigger than 1 at least, so that x is greater than 1. So over here x is greater than 1, so its absolute value, so for x, the biggest this can be is x equals 1, and then the bigger x becomes, the smaller this becomes. But it's always going to be less than delta over 2 times 1, because that's the biggest it would be. And this is smaller than delta. And then this is just the 2. So we can say that x minus 2 divided by 2 over the absolute value of x is less than delta over 2. That we can say. So now, if we want this to be less than epsilon, or in other words, if we want this to be less than epsilon, all we have to do is epsilon equals delta over 2, or or delta equals 2 epsilon. So let's just assume that. Okay, so we can erase all this. Let's assume that delta is going to equal 2 epsilon, right? So now we have the absolute value of x minus 2 is less than delta is equal to 2 epsilon. In other words, the absolute value of x minus 2, a half, is less than epsilon. In other words, but at the same time, we can also say, so if this is true, we can also say the absolute value of x minus 2 divided by 2 absolute value of x is also less than epsilon, because x is greater than 1. And so we can say the absolute value of x minus 2, let's first flip it, or in other words, 2 minus x, absolute value over 2x, absolute value is less than epsilon, or in other words, the absolute value of 2 minus x over 2x less than epsilon, or in other words, the absolute value of 1 over x minus a half less than epsilon, and we're done. So again, we assumed that x minus 2 is less than delta. We took delta to be that. We got our conclusion, so we got that. So the next problem that we are going to do is going to be problem 37. So we have that the limit as x goes to a, the square root of x is equal to the square root of a. This is what we're trying to prove if a is greater than 0. So what we want, we get x minus a is less than delta, then the square root of x minus the square root of a is less than epsilon. So this condition is the same as writing square root of x minus the square root of a times square root of x plus the square root of a over the square root of x plus the square root of a. It's less than epsilon. Or in other words, so we now can say that we want x minus a over square root of x plus square root of a, this absolute value, to be less than epsilon, right? Because we have x minus the square root of a times the square root of x plus the square root of a. This gives us square root of x plus x square root of x square root of a minus square root of a square root of x plus a. These are gone. Oh, sorry, this is a minus. Okay, so we get that. Or what we want is x minus a is less than epsilon times the square root of x plus the square root of a. So all we need to do is take delta equals epsilon the square root of x plus a. Which, by the way, because the delta is in terms of epsilon and x, this means that this is not uniformly continuous. I guess that makes sense. I don't know. Yeah, anyway. So now for the actual proof, right? So we're assuming delta equals epsilon square root of x plus a. So we're going to have x minus a is less than delta, which is equal to epsilon square root of x plus the square root of a, or x minus a over, this would probably be, well, it doesn't have to be absolute value because the x, this is positive and this is assumed to be positive, so whatever. Yeah. Anyway, absolute value, the square root of x plus and the square root of a less than epsilon, or x minus a over the square root of x plus the square root of a is less than epsilon, which, okay, let's just erase some of this. So now we get so we know that x minus a is equal to square root of x minus the square root of a times the square root of x plus the square root of a. So what we get is that square root of x minus the square root of a times the square root of x plus the square root of a over the square root of x plus the square root of a is less than epsilon. These cancel. We get the square root of x minus the square root of a is less than epsilon. That completes our proof. Yeah, very nice. So problem 39 now is an interesting one. We have a function. We already saw this function f of x is equal to 0 if x is rational, or if x is in Q, which means x is rational, and 1 if x is irrational. I'm just going to say x is in R. And we want to prove that the limit as x goes to 0 of f of x does not exist. That's what we're trying to prove. Let's write this nicely. F of x does not exist. So let's imagine, for sake of argument, let's suppose that the limit does exist. So let's suppose that the limit exists, that it equals some L. And we're going to show that there's a contradiction no matter what L we assume that f of x might be. So we have that the absolute value of x is less than delta. We'll have this statement, then the absolute value of f of x minus L is less than epsilon, right? Yeah. So now, well, one thing we have to say about the rational numbers and the irrational numbers is that no matter how close we get to 0, no matter what interval we make around 0, this is around 0. So we want, these are x's with a ball of delta around 0. So plus delta and minus delta away from 0, we're taking a bunch of x's. And we're claiming that no matter how close you get to 0, no matter how small you make delta, well, first we're claiming that you can make delta small enough such that f of x minus L is less than epsilon. But this statement, which we're saying is true for the sake of contradiction, is clearly false, because that no matter how close you get to 0, you're always going to be able to choose x's, so x from the interval negative delta, delta, you'll always be able to choose x's such that x is either in rational, or x is irrational, meaning no matter how small you make delta, you will always be able to find x's in the interval negative delta, delta, such that x is either rational or irrational. You get to choose depending on what x you choose. And for the rational ones, it's easy to see this. Just whatever delta is, take 1 over n, where n is really, really big, and 1 over n will be smaller than delta. You can choose, for any delta, you can choose an n such that 1 over n is smaller than delta and bigger than 0, so bigger than negative delta, and so that number, 1 over n, will be in this interval, and it will be a rational number, 1 over n. For the irrational numbers, I am not currently going, okay, so you can say, take the square root of 2 over n, which is an irrational number, make n again really, really large. For any delta that you choose, you can make n so large so that this is less than delta, and it's greater than 0, so it's greater than negative delta. So again, so for the two numbers, so no matter how small, so we can make the statement, no matter how small you make delta, you can choose two numbers, x in the interval negative delta, delta, such that, so if you want a rational number, you can choose 1 over n for n really big, and that will be x equals 1 over n, and that will be your rational number. If you want an irrational number, you'll choose x equals the square root of 2 over n. That will be your irrational number. So you can always choose either a rational number or an irrational number. And then no matter what your L is, right? So if your L, so L can be a bunch of things, but let's first assume that L is equal to 0. Let's say L is equal to 0. Then what you're going to do is you're going to choose x to be the square root of 2 over n, for n big will be a irrational number. So you're going to have f of x for an irrational number, which is 1, minus 0 is less than epsilon, or in other words, 1 is less than epsilon for any epsilon, and that's not true. I'm going to take epsilon to be a half, and this is not going to be true. So this statement is not true. But we are assuming, because we're assuming that the limit exists, that this statement is true. We're assuming that this statement is true. And if we assume that this statement is true for a chosen delta, then we are assuming that no matter how small we make epsilon, we will always be able to choose a delta which will satisfy this equality. And yet, you can make delta as small as you want, and then take an x which is irrational, and then you're going to have, and then choose epsilon to be a half, because you get to choose whatever you want for epsilon. Epsilon should be able to get as small as you want it to get. So you're going to be able to choose epsilon being a half, which makes this inequality false. And because it will say something like 1 is less than a half, which is false. This is assuming that L is 0. But L does not have to be 0. I mean, I'm assuming maybe it's not 0. Maybe L is 1. So let's look at L equal 1. Maybe L is 1. Who knows? Well, if L is 1, then again, I provide the epsilon. I get to give the epsilon. So I'm going to say, okay, I want epsilon to be a half. You provide the delta. Okay, you provided the delta. Really, really small delta. You gave me a delta. Then I argued that I can take an x, which is still in the interval that you provided. You made delta really, really small. Really, really small. And yet I can still take an x from the interval that you provided with your deltas such that that x is in Q, is rational. And then I'm going to say, okay, well, f of that x is 0. So I'm going to have the absolute value of f of that x for that particular x, which is irrational but still in the interval of deltas. That particular x is less at minus 1. Well, you're claiming that that is less than epsilon, which for us is a half. For that particular x, we're going to have 1, because that x is rational. So we're going to have the absolute value of 1 minus 1. Sorry, I keep making this mistake. Again, that particular x is rational, so the f of x for it is 0. So 0 minus 1 is less than a half, or in other words, the absolute value of negative 1 is less than a half, or in other words, 1 is less than a half. Again, not true, a contradiction. So this statement is not true. So that's for L equals half. Now L can be any other number. It can be any other number. Now we're assuming, well, L is not 1 and it's not a half, because if it's 1, we have a contradiction. If it's, sorry, it can't be 1 or 0, because if it's 1, we have a contradiction. If it's 0, we have a contradiction. So now let's take, I don't know, L can be anything else. L can equal anything else, although a constant, anything where, but not 1 or 0, not 0 or 1. Well, if that's the case, then we're going to have, well, take x to be anything you want, rational, irrational. Let's assume that we're going to take it to be rational. And again, I'm going to take epsilon to be a half. I'm going to take x to be rational. You can choose whichever one you want. You're going to have f of x, where x is rational, minus, I'm not going to choose epsilon to be a half. I'll tell you what I'm going to choose epsilon to be. F of x minus L, whatever that L is, but it's not 1 or 0, is less than epsilon. Or in other words, 0 minus L, because that x is irrational, is less than a epsilon. Or in other words, L is less than epsilon. And now I'm just going to say, well, I want epsilon, whatever you chose L to be, I want epsilon, and I can do this because epsilon is for all epsilon. You get to choose one L. You can't choose a bunch of limits. You have to say a specific limit. You claim it's a specific limit. I get to choose as many epsilons as I want. It's a little tricky keeping track of who chooses what and when you can change your choice, and that can be a little tricky, but the definitions are very beautiful and elegant and work. So just understand what you can choose, when you can choose, what gets to change. But epsilon can change. I can take any epsilon I want. So I'm just going to take epsilon to be whatever it is. I'll just take epsilon to be less than L. Whatever. You gave an L, that's your limit, and I'm just gonna, I can choose any epsilon. I can choose epsilon can equal 1, 0.0001, and any number. It can be 1 over a million for all I care. Epsilon can be any number. So if L is some number, some positive number, no, L could be negative too because you have an absolute value here. Okay, so I'm going to choose epsilon to be the absolute value of L. Whatever you think L is negative, you think it's positive, I don't care about that. I'm going to choose epsilon to be the less than the absolute value of L. But in that case, this is not true, that L is less than epsilon. By definition, I chose epsilon to be less than L, which I'm allowed to do. But you went through your logic and you got, well, L is less than epsilon, which is impossible. And so, again, this statement is false. So assuming this statement, you get contradictions. So you cannot assume this statement. And the intuition behind all of this is pretty simple. You have your function. It's 1 for all the rational numbers. It's 0 for all the irrational numbers. No matter how close to 0 you get, you're going to always have rational numbers and irrational numbers. So you cannot really say that your limit is 0 because there are a bunch of numbers here that don't approach 0. There are a bunch of numbers that come from x's being rational, which don't approach 0. You cannot say that your limit, so that's why you can't say your limit is 0. You cannot say that your limit is 1 either, because there are a bunch of irrational numbers, in fact, more irrational numbers than rational numbers, which are getting closer to 0 and not to 1. And you cannot say that your limit is a half or negative a half, because that's just absurd. No points are going towards any of those. So your limit can't be 1, it can't be 0, it cannot be any other number. So the limit does not exist. Well, I'm out of time, and I don't really want to do any more epsilon delta definition stuff. Everything else, just problem 40. Problem 40. What is theorem 1 in section 2.3? I don't know. Section 2.3, theorem 1. I believe that it's every polynomial, the rational function has that limit. That shouldn't be hard, just brute force, epsilon delta definitions. Everything else after that, problem 41, 42, 43, and 44, they're all using definition 6. Basically, find a delta that makes f of x bigger than m. Should not be too hard. The next video is going to be about continuity, the definition for continuity, and I'm just going to go through the problems in section 2.5, and that hopefully will just take a single video. And after that, I guess I'm going to move on to the definition for derivatives and derivatives. Okay, hope this was helpful.